the people who sent in the survey that Julianne sent out, the overwhelming majority of you picked either metabolism or light and optics. So we're going to do light and optics today, but we'll probably try to get another one of these meetings together to do metabolism soon. Metabolism just requires a little bit more planning from my perspective because I'm used to, like we said last time, used to talking through all this stuff with people one-on-one sort of, and it's a little bit harder just to lecture from it. So it's hard to determine like in what order we need to move. Whereas whenever we're in tutoring meetings, I can just ask you questions and you ask me questions and go off of those. So also, and I'm not sure if how much I emphasized this last time, but if any of you have friends who are prepping for the MCAT or know anybody prepping for the MCAT, even if they're not your friend, you're welcome to invite them to these. The part of the reason that we're doing this is just to in addition to adding value for all of you who are working with us, is to try to raise awareness of what we're doing without having to spend like all of our money on Google Ads. So, and you're welcome to send out the videos to other people as well. I'm just trying to add value here. So like I said, we're going to go through some light and optics stuff. Sam is joining again. He's also going to interrupt me periodically to go over some things that he has that he thinks will be useful for light and optics. Some of the feedback that I received last time said that a few of you would prefer if we had some practice questions to like illustrate some of the stuff we're talking about. So I included a few MCAT discrete style practice questions that we'll also go through during this thing. And so we'll use those as kind of a catalyst for discussion. You're also, like last time, welcome to send messages in the chat. Sam can respond there. Or if many of you have the same question, then he can just interrupt me and go with your questions from, and we can address some of the questions in real time. Any of you are welcome to unmute and tell me if you have any questions too. Like if there's something that's really pressing that you think others might have questions on, or if you think I misspeak or something like that, I'm happy to do that. Anyway, so I think that that's pretty much it from a housekeeping perspective. I burned like 5 minutes saying all that. So I think we've given people enough time to join. And I'm sure people will join throughout, but I'm going to go ahead and get started here. The hardest part about the light and optics content on the MCAT, I think, has to do with the geometrical optics, probably for most people. So we're going to spend a decent amount of time talking about that here, but I've started out just by including a few definitional things that I think can be helpful for people to just be aware of, because I think that part of the issue with this that students frequently have is not being sure what we're talking about when we say like a focal point or a curvature of the lens or curvature of the mirror or something like that. So I just wanted to include those off the bat. First and foremost, the curvature component of this is what the curvature component is referring to is that if you pretend that the lens or that the mirror or whatever it is, the interface between the media is something that could potentially go out and form a complete circle or a complete sphere. So like imagine let's say we've got a mirror that's like this. The curvature of this mirror could be assessed if you imagine that this mirror goes out and forms like a complete circle. And so like we would look at that complete circle. And so like this sort of would be the curvature of that mirror. And so if we look at that curvature, now that we've formed a circle, we can also see that this circle is going to have a center, right? Like any circle. And so the center of curvature is just referring to the center of that imaginary circle that your interface formed. In this case, since we're imagining this is a mirror, you can say the light is probably coming in and bouncing off the mirror like this, right? So your object would be over here, and then your image is going to be wherever the image forms. We'll come back to that sort of thing in a second, or wherever the light rays converge is where the image forms. So we'll come back to that in a minute. But referencing this curvature, you could also have a case where you imagine that the person or the object or whatever is in the center of the circle or in the middle of the circle somewhere. So like inside of the circle. And in that case, we just take the opposite perspective. And now, the light is coming in toward the interface like that. And so it's just as if you have like a concave mirror in that case, right? So we can look at convex, concave, either way, the surface can form a complete circle. The reason I'm beating that into the ground is that the focal point and really everything about that lens or about that mirror, how much it refracts light or the angle at which it reflects light is going to have to do with the size of the circle. So if the mirror or the lens forms a circle, then we can look at the radius of that circle as being a really important factor in determining the strength of the lens or the mirror. So here, this is like the radius of curvature at that point. You can see I define it up here. And I can set all of these notes as well. So radius of curvature is just like halfway across that imaginary circle that the thing forms. And then the focal length, importantly, and this is something that I didn't even know until like pretty recently, embarrassingly recently, is the actual formal definition of the focal point. So the focal point is always going to be the point at which parallel light rays will converge after they interact with the lens or with the mirror. And so it can be where they converge in real life or where they converge in fake life, but it's where parallel light rays will converge is the focal point. And that is always going to be at a spot along the radius of curvature that is exactly halfway between the interface and the center of the circle. So this radius line that I drew over here, you could say that the focal point here would be like right here at that spot. But that's only if the radius that we're talking about is parallel to the light rays that are coming in, because we said that the focal point has to do with the spot where the light rays are going to converge after they interact with it, right? So we can imagine that if we have parallel light rays parallel to that line, let's just draw them as these blue light rays right here, that they're going to end up converging at this spot, at this focal point, right? Because they're parallel to that. So like if I draw on the light rays as maybe coming in over here, right? So these light rays are parallel to one another as well. Those are not going to converge at this focal point. That doesn't make any sense, right? We'd have to draw another like radius line that is parallel to those. So just wanted to emphasize that, like a formal definition. I just find it to be somewhat helpful. And we can come back to that stuff in a second too. But again, just giving you definitions, I think is useful. Then obviously the object is the thing that is being seen through the lens or the mirror. And so it's where the light rays start is how I like to think about the object. It's just like where the light rays begin. And then the image is wherever the light rays converge, as I mentioned before. So the image could be at the focal point if you have parallel light rays, or it could be somewhere else. Anyway, those are just, again, like I said, definitions to start. The way that I really like to start thinking about all the lens and the mirror stuff, all the geometrical optics stuff, is with respect to a flat lens or a flat mirror. And the reason for that is just it's the simplest possible version. So if we were talking about curvature before, what would be the radius of curvature of this flat lens or this flat mirror that we're putting out here? The radius of curvature of this thing, if we tried to draw it out like we did the other one, if we were to try to take a radius of curvature, let's say this side on the left is like our reflective or our refractive surface. If we try to draw out the radius of curvature, we would try to say like, okay, well, let's just draw. That's not what I meant to do. Let's say that like, let's just draw that, like click on the line and trace it out until they come back around to form a circle, right? But because this thing's perfectly flat, those lines are never going to come back around. Like they will, but just at point infinity. Okay, so that means that this flat lens or flat mirror, or if you see it, you can see it called a plane lens or a plane mirror as well, meaning like a flat plane. The flat plane or flat lens, flat mirror is going to have a radius of curvature of infinity. And so what that means is that the focal length on that same mirror, that same lens, is also going to be infinity. That has some interesting implications when you get into this 1 over f equals 1 over I plus 1 over O equation, right? Because if we say that f, the focal point, exists at infinity, then what that means is 1 over infinity. Well, if you think about like what 1 over infinity is, if you think about 1 over 1, that's 1, right? 1 over 2 is 1/2. 1 over 10 is 1/10. So as you make the denominator of a fraction bigger, the number that you're referring to is going to get smaller. So 1 over infinity effectively just equals 0. So now what you have is 1 over I plus 1 over O equals 0, right? So all that tells you is that I and O are the same. They're just opposites of one another. So one has a negative sign, one has a positive sign. We'll come back to doing these sorts of calculations in a second. I just wanted to emphasize the idea of what you do with the focal length in a plane mirror or a plane lens. You just treat it as infinity. So looking at this thing, this block of glass, let's say that we have, we'll imagine that it's a mirror first, just because this is probably like the simplest example in all of the geometrical optics. So if we imagine a light ray coming in at this mirror, we'll just say it's coming in like this, then how is it going to reflect off of the mirror? How do you think about that? If you're familiar with, if you've reviewed light and optics at all recently, you'll probably already be aware of the fact that it bounces off the mirror at about the same angle, or at the exact same angle that it comes in to hit the mirror. But the challenge here, that the pitfall that I think a lot of people can run into if they just look at this and be like, oh yeah, that's easy, it bounces off just like it came in, is like, what is that angle referring to? Is it this angle between the light ray and the mirror? I mean, technically that is true, right? Like θ1 and θ2 are the same thing here, but this is not what it's referring to. So I want to take this opportunity to establish a convention that all of our angles that we talk about with respect to light and geometrical optics are going to be between the light ray and the normal line. The normal line being the line that is perpendicular to the interface of the two media at the point where the incident ray hits the medium, right? Or at the point where the ray hits it. So like right here, this is the point where the incident ray is hitting it, right? I just made it like darker. And our normal line is just going to be perpendicular to the interface here. So because this is a flat line, then our normal line just has to be perfectly horizontal right here. And so the angles that we're going to be referring to this whole time, again, are just with respect to the theta 1, we're going to say is going to be with respect to the incident ray and the normal. And by the way, when you see incident light ray, it just means the thing that's hitting this the surface, like the thing coming in originally. I wish that people just define terms like that. So the theta 1 here is the angle between the incident ray and the normal. And then theta 2 is going to be the angle between the reflected ray and the normal. And so in the case of a plane mirror, a plane mirror, or really any mirror, once you've drawn the normal, the incident angle is just going to be equal to the reflected angle, and that's all there is to it. So relatively simple. Refraction is a little bit different. So just like reflection is bouncing off of the interface, refraction is going to be going through from one medium into the other one, but light bending as a result of that. How does the new medium cause light to bend? Like, what is the phenomenon underlying light bending? So yeah, thank you. Yes, okay, so index of refraction. Thanks, Alyssa. Index of refraction refers to how fast light travels in that medium with respect to the maximum speed light can go. So the maximum, when I said speed, I meant velocity. The maximum velocity of light is going to be achieved in a vacuum because it's the least dense thing. And so there's the least impedance on the light as it moves through a vacuum. And for the MCAT, we're just going to say that is equal to C, which is 3 times 10 to the 8 meters per second. Okay, so the index of refraction, which Alyssa referred to, that is N, is always going to be the velocity of light in a vacuum divided by the velocity of light in the medium. I'm just going to call it VM here, meaning velocity of light in the medium. And so for everything, you can imagine that this number cannot possibly get less than 1. If speed of light in a vacuum is the fastest light could possibly go, this number can't be less than 1. So it's always going to be 1 or greater. For error on the MCAT, we just refer to it as 1, and that's usually the place where light's starting. Don't take it completely for granted, but when in doubt, you can use 1 as probably like your first velocity or your first refractive index. And then for anything denser than air, we're going to usually have a higher refractive index than 1. So if we were to say, let's imagine that we've got some glass here and that we measured the refractive index of our glass to be like 1.6. Actually, let's just say 1.5. We measure the refractive index of our glass to be 1.5. So what would be the velocity of light as it goes through that glass? Well, if we want to do this, so we said it's 1.5, which is the same as 3/2. Right. So we know that C is 3.0 times 10 to the 8. And if it's 3, and right, then the thing below it is 2, then what we can say is that velocity of light in that medium, I'm just going to draw an arrow instead of an equal sign. So VM is 2 times 10 to the 8 meters per second for a refractive index of 1.5 or 3/2. All right, so that's just this arbitrary number that we're going to give to the glass that we're moving through, just so we can think about how it changes the angle of light as it moves through the medium. So here we've got our light ray coming in. I'm just going to draw it a little bit further down on the same glass here. So it's coming in on this glass. We go ahead and draw out our normal line, same as with reflection before it. And then we start to think about, all right, well, what is, if we've got out here in air, we'll say N1 equals 1.0. And we already know that N2, we just said, is equal to 1.5. All right, so we want to ask ourselves first and foremost, like, is the light going to bend toward or away from the normal line? The equation that you need in order to determine that is called Snell's law. And it's just essentially going to be a ratio of refractive indices with compared to a ratio of sines of the angles. All right, so you'll frequently in most textbooks see the equation written out as N1 times sine of theta 1 is equal to N2 times sine of theta 2. If that's what you have in your head already, just keep that in your head. It's probably fine. But if you want to take a little bit of a shortcut whenever you're solving these problems, most of the time it's a little bit better to write this equation as n1 divided by n2 is equal to sine theta 2 divided by sine theta 1. This is almost always going to be the the way that you end up using the equation. So if we look at this, and I'll just arbitrarily give us like an angle of 45 degrees right here. So we'll say theta 1 equals 45 degrees. Is theta 2 going to be bigger or smaller than theta 1? And here you might be able to already see how the thing that I'm giving you is a little bit better than like the Snell's law that you'll see in the textbooks. Again, this is no great feat by me. This is algebra. You've all been able to do this for like a decade already. So, but you can see that n1 being 1.0 and n2 being 1.5 tells us that sine of theta 2 is going to be a smaller value than sine of theta 1, right? And so if the sine of the angle is smaller, and we know the angle is less than 90 degrees, then that means that the angle itself is also smaller, right? So we know that theta 2 is going to be a smaller angle than theta 1. What that tells us is that the light is bending toward the normal line, right? So what we can see here is that light, since theta 2 is smaller than theta 1, light has to bend up toward the normal. That's not significant enough. So here our light is bending, it's a little exaggerated, but light is bending up toward the normal here. So that in this case, and remember, we always form our angle with respect to the normal line, the light ray and the normal line. This is something people miss a lot. Like they'll see the light ray go through the interface between the media and then not be sure what they should assign as the new angle. They'll be like, okay, well, is it that one, or is it this angle? Or, you know, like my light bends toward the normal, but does that mean that it goes like this, or does it go like that? Or is it bending toward the interface? People get that confused all the time. You always want to compare the incident light ray or the refracted or reflected light ray with the normal. That's your only point of comparison in all of this. So this is theta 2, and we know now that theta 2 is smaller than theta 1, but what is theta 2? Who can calculate sine of 45 in their head? Probably nobody. I mean, I'm sure a lot of you have it memorized, but what I usually recommend for MCAT is just knowing a couple triangles. So being aware of the 30, 60, 90 triangle and the 45, 45 triangle. You probably all have heard of SOHCAHTOA at some point. I just think is a relatively good way to remember this stuff. So we have this 45 triangle, then we can say that these two sides are identical to one another. And if each of those is just one, you can use the Pythagorean theorem to calculate that this is radical 2. And sine being opposite over hypotenuse. So sine of a 45-degree angle, right? Because we said this is 45 degrees. Sine of 45 is just going to be opposite, which is 1 divided by radical 2. So 1 over radical 2. I recommend for the MCAT memorizing that radical 2 is like 1.4. It's just a good number to be aware of. So 1 over 1.4 is roughly what that is. We already know that n1 divided by n2 is 1 over 1.5. So again, just further confirmation that this is going to be slightly different than that, right? Okay, so then the other triangle that you need to be aware of that I just mentioned is the 30, 60, 90 triangle. That looks ridiculous. These are hard to draw. The 30, 60, 90 triangle is just going to give you sine values for 2 more points. And then you can kind of just be aware of like where sine of 30 is, where sine of 45 is, where sine of 60 is. And then you can also reason out where sine of 90 is as well. And I'll show you that here in just a second. So this is 60 degrees. Then we make the small side 1. I'll tell you that the hypotenuse is twice as long as the small side for the 30, 60, 90 triangle. And so then you can just use Pythagorean theorem to find the longer side, which is radical 3. And so the sine of a 60-degree angle, sine of 60, is going to be equal to radical 3 divided by 2. Sine of 30-degree angle would just be the opposite, so it's 1/2. Right, so with that, we can go ahead and find roughly what our theta 2 is here. So we said 1 over 1.5, and then we've got sine of theta 2 over sine of theta 1. We said theta 1 was radical 2, or 1 over radical 2, right? So 1 over radical 2 is the same as like multiplying it by radical 2 over 1. So if we multiply this side over here by 1.4, then what we'll find is that our sine of theta 1 is some number between, I don't know, it's probably like the sine of theta 1 is going to be a little bit bigger than 1/2, but definitely smaller than the 1 over root 2. So I recommend using answer choices to guide you on this stuff. Just find like which 2 years is between and which one that's a little bit closer to, and then just picking it, moving on with your life. One question that I could see the MCAT kind of asking about, because it's not going to be as directly taught as what we were just talking about, is what the angle of this thing is as it comes out of the other side of the glass, like on the opposite side. So we were assuming this is just like a giant block of glass. So the light bent toward the normal while it's going through the glass, but then it's also going to have another medium shift whenever it comes out of the glass. So we're moving from a denser medium to a less dense medium. So based on that alone, you can assume that the light is going to bend away from the normal line. We have to establish a new normal line here. So here's our new normal. And at this point, maybe we'll make this one like green or something. At this point, we can say this is our theta 1, right? And the light moving away from the normal line means that our theta 2 is going to have to get bigger, which makes sense given the equation. And so we can say that we can see it like take off down this direction. So this would be our theta 2 in that case, or green theta 2. Importantly, one thing that we can recognize is that given that these two interfaces of the media on the two different sides were both vertical, we're both like perfectly vertical with respect to one another, then we can say that theta 2 over here on the green side, theta 2 of the green side is going to be equal to the same thing as theta 1 on the opposite side, because we bent back toward the normal first, and then we bent away from the normal with the same degree of bend, because the difference between the refractive index of the first medium and the second medium was the same in both cases. And we could come up with a mathematical proof of that. This is where this is hard, because I'm not sure how many of you get what I'm saying on that, but probably going to go ahead and just keep going unless this is, please object vehemently in the chat if you would like me to elaborate on that more. So now that we've talked about the flat lens and the flat mirror, the only change that we need to make to start considering these harder problems that show up on the MCAT is to account for the curvature of the thing. So coming down here, I'm going to draw a circle really quick. All right. So if we look at,
Joe.
Yeah, go ahead.
Anastasia is wondering if you could re-explain what you just did, just like a recap.
Do you mean like?
Is it okay if I talk?
Yeah, go for it.
Okay, sorry, I didn't want to interrupt you. Okay, could you just like re-explain how you knew that theta 2 would be the same value as theta 1?
Yeah, for sure. Yeah. So
could you explain that, please?
Yeah, absolutely. Okay, so I knew that.
Okay, thank you.
This like new angle that we take whenever we leave the medium, like when we go from glass to air, what we would do here, I'm going to scroll down here and give myself just a little bit more room. I think it's going to make this a lot easier, because I was trying to condense it in that small amount of space, and I didn't explain it very thoroughly at all. So thanks for calling me out on that.
It's okay. You did a good job, but
all right, thanks. Well, okay, so whenever the first light ray is coming in, we have an angle of 45 degrees, and we're going from, we'll call this new side over here 3. Okay, so we'll say in 3 and sine theta 3. Okay, like on the opposite side of the lens. So at this point, we have n1 is equal to 1.0 and theta 1 equals 45 degrees. And we've got our n2 is equal to whatever it was, like 1.5. And theta 2, I wish I had like an exact value for this, but we could say maybe theta 2 is like 35 degrees. I'm just going to make up numbers. Don't check this on a calculator. It won't be exactly right. Theta 2 is 35 degrees. Now, if we want to think about what our N3 is 1.0 as well, right? And theta 3, because N3 is 1.0, and we know that N1 times sine of theta 1 equals N2 times sine of theta 2. And now we're starting with N2 times sine of theta 2, which are the same numbers that are in this equation. And so in order for this equation to be true, and this is also going to be true, right? N3 times sine of theta 3 is equal to N2 times sine of theta 2, because those are the two that are interacting on that side. In order for all of this to be true, and for N1 and N3 to be equal to one another, right, which they are, that tells you that theta 1 and theta 3 have to be equal to one another, given this equation. Does that maybe make a little bit more sense?
Yes, thank you so much for explaining that.
Oh, yeah, no problem. Okay, so if we have a convex lens, I'm just going to maybe we'll just think about one side of it. So convex lens here, and the reason I'm picking this one is it's probably the most likely thing to be tested, because it is what your eyeball is a convex lens. So we're going to say that we have parallel light rays coming in. And actually, what the MCAT would tell you is not that they're parallel light rays. The MCAT would probably say, hey, we've got light rays coming in from an object that's like really, really far away. Okay, and when it says like really, really far away, that's how they would word it. What they mean is that the object is so far away that when the light rays spread out from the object, So we'll say let's compare an object right here. Like we'll call this far object and we'll call this near object. Let's say that in both cases, we want to look at the light rays that are going to hit at these 2 points. Light rays from this near object are going to have to take a pretty significant angle to get to those 2 points, angle away from one another, right? Because all we care about is angle with respect to the normal. So this angle is pretty significant. Whereas light rays for the far object don't have to take nearly as dramatic of an angle. And so they're closer to parallel. So you can imagine as the object gets further and further and further away, the light rays become closer and closer and closer to parallel, right? So if you're thinking about really far away object, just general rule for the MCAT, if it tells you object real far away, right? Like if it doesn't give you an object distance, treat the object distance as infinity. That's the same thing as saying that they're really far away, right? You can also cheat there because then you can know if object distance is infinity, then image distance is the focal length. Okay, just a little hack on that. Okay, so we're going to be thinking about object really far away here, meaning that the light rays are coming in parallel to one another. All right, so I'm going to draw this one on top first. We're going to say, all right, here's our light ray coming in, and we'll draw one on bottom down here too. So they're parallel to one another. Now, we want to think about what happens when they hit this lens. We're going to use the exact same process that we just went through above, except here there's one tiny little extra step that we have to do. The only tiny little extra step is we have to figure out, right? Because with respect to the one up here above, the first thing we figured out is where our normal line is, because all of our angles are with respect to that normal line, right? So here we need to figure out where the normal line is. The problem is that we have a curved surface. So our normal line needing by definition to be perpendicular to the interface of the media, it really matters where we're hitting the medium on this curved surface, right? Where we're hitting the interface. So in order to draw our normal line, the first thing we need to do is establish what the slope of the surface is. So I always recommend just like eyeballing a line that's sort of tangent to the interface of the medium. So you could say maybe like this sort of, that might be tangent at that spot. I've been having this bug the last couple of days too. I don't know why these lines are disappearing. Okay, there we go. So maybe that's tangent to the interface. So at this point, we can say our normal line having to be perpendicular to that is something, don't judge my drawing on this either. This is hard. It's probably something like that. Is that close enough? That's good enough for me. So we would call this our theta 1. All right, now remember theta 2 is always going to be with respect to the normal as well. And it has to cross the interface. It also has to cross the normal. So this is not theta 2. Right? This is important. We're coming through the interface, we're crossing it, we're also crossing the normal line. So that doesn't work. Theta 2 is going to be on the top side of the normal line because theta 1 was on the bottom side. Now, if we imagine, let's say that our refractive index here N2 in this case equals, I don't know, we'll just go with 1.4. That's one you'll see a lot because that's like the refractive index of water. So if N2 equals 1.4, N1 equals 1.0, we know that the light has to bend toward the normal, again, because we're going from less dense to more dense medium. And so you can say, all right, well, light ray bending toward the normal's also sloped down. So this light ray is probably going to slope down like this as well. And if we do the same thing on the other side, so we draw the tangent line right here, something like that. Okay, great. Thank you. And display. We draw the tangent line like right there. Then we can draw our normal line perpendicular to that again. And then we can recognize same thing is happening, right? And so our light rays converged right here. Given that that's where they converged, this is our image on this side. So now we need to think about whether this image is a real image or a fake image. Whenever I say fake image, what I mean is virtual image. I just do it that way in my head. The way that I think about this for the MCAT, and there's some tables in the Kaplan book and pretty much any other textbook that you could ever find that are, in my opinion, worth memorizing for this test. But if you do happen to forget what you're looking at, Angela, I just saw your message in the chat. The answer is no. No, the error is 1, but they'll give you anything else. But I would say know that the refractive index of the error is 1, and they'll have to give you something, or they'll tell you what the speed of light is in that medium, and you can use that to calculate the refractive index. So if you're thinking about whether you have a real versus a virtual image for lenses and mirrors, just trying to think about where you would expect the light to go. So in the case of a mirror, you're going to expect that light to bounce back, right? So if the image forms in a place where you would expect that light to go, then you can say it's a real image. So in the case of a mirror, yeah, Humira, that's right. So in case of a mirror, you would expect the real image to form on the same side as the object. In the case of a lens, like in this case, we expect the light to go through the lens, right? So we expect the light to show up, to converge on the other side of the lens from the object. And so a real image is going to be on the opposite side of the lens from the object. So that's how I would think about this. So converging mirrors or converging lenses form real images. Converging mirrors form real images, because those are the two that make the light rays converge together on the same side you would expect them to converge. If the light rays don't converge on that same side, in the case of diverging stuff, right, then you will then they're converging in virtual space or in fake space. And so those are virtual images, or in the way that I word it, fake images. I just think that that's a useful way of thinking through this stuff. So that's how I would recommend you thinking about light moving through interface, moving through lens, moving through a mirror, or not through a mirror, but bouncing off of the mirror. It's just using that sort of logic and really memorizing the signs from the lens equation that I gave you up here earlier is useful as well. This one right here. This equation is crazy useful for this entire test. So like most of the questions you run into will be using that equation. We'll look at some of them here in a second. Sam, did you have something about this that you said helps you remember it?
Yeah, is it okay? Yeah, I was gonna just like illustrate it really quick. Is it all right if I like share my screen?
Yeah, go for it.
Do you guys see that?
Yeah, we can see
Okay.
it.
So disclaimer, this is just a mnemonic that I use, and whenever I think about like optics and like ray tracing problems. This is not meant to be like a replacement for like a good foundational knowledge of this content, but it's just something that can save you time when you're dealing with like maybe less intense questions related to optics. So it's a pretty simple mnemonic. So if you imagine just like a converging mirror here, and then if you I'm gonna have like the focal point here and the center here. If you kind of divide these into 3 different areas, and this just has to do with the object being in a certain area. If you have the object, for example, on the very left here in this first region, where it's past the central point of the mirror, it's going to be, the image produced is going to be smaller, inverted, and real. If you have the image, okay, so that here, this little guy right here is going to be produce an image that is smaller, inverted, and real. If you have something here, like an object in between the center point and the focal point, it's going to produce a larger image that is also inverted and real. And then if you have an object here that is in front of the focal point, it's going to again produce a larger image, but instead it's going to be upright and virtual. So the mnemonic that that we use is kind of cheesy, I know, it's just Sir Lure Love. I don't know if, yeah, I think someone mentioned like SUV, and that's like for diverging lenses and mirrors. That's part of this mnemonic, and so it's just kind of a shortcut to like just quickly knowing, all right, if it's past the focal length, like as in this object here, then it's going to produce a larger image that's inverted and real. If you have an object that's in front of the focal length, it's going to produce an image that's larger, upright, and virtual. And we can illustrate the ray diagram and kind of like prove that, but that's probably not super necessary. And so this is that's for diverging and converging. And then for diverging lenses, you don't have to divide the area at all, because any object that's going to be hitting a diverging lens or mirror is just going to be smaller, upright, and virtual. And that's kind of what someone was talking about in the chat. So this is the mnemonic for diverging, and then for converging, it's going to be this guy.
Yeah, Samir, did you have a question?
Yeah, so these mnemonics are for mirrors, or are they also for lenses?
They're for both.
Oh, for both. Okay.
Yeah.
Okay.
Yeah.
And I was just wondering, there's a point where there's no image formed, right?
Mm-hmm.
I'm not sure if that's at the center of curvature or the focal length.
The focal length.
Okay, great, thanks.
Yeah.
Nice. Yeah, and the reason for that is if you imagine like, you know how I said earlier, the parallel rays coming in will converge at the focal length. You can think about that same idea just backwards, that if the rays are coming from the focal length, they're going to leave as parallel, meaning that no image will ever form anywhere because they'll never converge together. You could also write your image distance as infinity in that equation if you wanted to do calculations with respect to that. So yeah, good question. Angela, did you have one?
Yeah, I'm sorry, I know you mentioned it, but would you mind drawing the rays for those? I was a little confused about just where everything would like,
Oh, for Sam's thing?
yeah.
Yeah. Sam, do you mind doing that just because you already have it drawn out on your thing?
Okay.
Yeah, or hold on, okay. There's
Yeah,
actually like a ray
fine.
tracing diagram, like a simulator. I'm gonna share this right here. You guys see that?
Yeah.
Okay. All right. So, so
That's-
2F is just the center point of the mirror. So just in case you were confused about that. So yeah, so this is just illustrating kind of where the rays would converge if you had the image at any one of those 3 points. So just as a reminder, the 3 rays that you can draw to form or to find out where the image is number 1, you can draw this parallel line here. Do you guys see my mouse, by the way, to see where I'm
Yeah.
pointing? Okay.
Yeah.
Yeah, so you can draw this top one here that starts out as parallel to the center line, to the mid, whatever it's called, and then going through the focal length. The second one that you can draw just hits the center line at the mirror and then reflects back at the same angle that it came in as. And the third line that you can draw is first through the focal point and then parallel back through. Right. And honestly, and actually, you don't even need to draw all 3. You can just draw 2 of them, and that's going to be sufficient for you to find where the image is. But that's the 3 that's possible for you. So you can just pick 2 that you like and memorize those in case you ever need to draw or to do ray tracing. Yeah. And so this so the image or the object here is in this like very leftmost region that's behind both the focal point and the center point. And you can see here that according to the mnemonic, the image should be smaller, inverted, and real. So the image here where all the light rays converge, it's a smaller image. And you can see that because all of the light rays that you draw that are according to the ray tracing rules converge at this point. If you were to move this image or this object to in between this, so the second region here, in between the focal point and the central point, then the image becomes farther away, like over here now. So it's larger, which is what you'd expect with the mnemonic, but it's also inverted and real. And then as you move into this third region here, so we can kind of also see how if you have the object right at the focal point, you're not going to make an image because the rays are not going to have any point at which they intersect altogether. And so you're not going to be able to form an image. So it's just impossible. So that just kind of is an illustration of that, what I think Samir was talking about. And then if you go into this third region here, you'll notice that actually with a converging mirror like this, the light rays are not actually going to be converging on the side of the mirror that you would expect. It converges kind of like if you were to theoretically draw the lines out on the other side of the mirror, it would end up at this point right here on the other side. And so according to the mnemonic, the image would be larger, it would be upright, and it would be virtual. And virtual by virtue of the light rays being on this opposite side here of the mirror, of where you would expect the light rays to, normally intersect. Does that kind of help with like visualizing it a little bit?
Yes, that was perfect. Thank you, Sam.
Okay, cool.
Yeah, that's a really cool tool that you have there. That's neat.
Yeah, this is I mean, I like had to do this for a lab in like Gen Phys or something. So this is
Nice.
where I got that from, but yeah.
Nice. Awesome. Yeah, no, I think that's really good. Cool. I think the ray diagrams were something that whenever I was studying for the MCAT, I had the hardest time with that. That drove me absolutely crazy. One thing to note on the ray diagrams for all of you, you're not going to have to draw them on the test. You know, like, I mean, you might have to get something out really quickly to try to help yourself think through a problem. That's fine. But you're not going to be graded on the MCAT on your ability to draw ray diagrams because this is a multiple choice test. Just so you know. Yeah. But no, and that's not to take away from anything you're doing there. I think that that's really important to understand how they work. But I just didn't want anybody to spend sleepless nights trying to figure out how to draw ray diagrams. If you are in that situation, we can probably send you the URL for the thing Sam was just using. Does that require a login or anything?
No, I literally just Googled like ray tracing
cool.
simulator.
Nice.
I'll just put it in the chat, I guess.
Okay, perfect. Yeah, thank you. From my experience, I use that equation, the 1 over all the stuff equation, to solve like most problems on this stuff on the MCAT, just so you all know. So we're going to do some practice problems with that here in a second, or here in a little bit, but I just wanted to emphasize that if you have a hard time drawing those, you're not going to lose on the MCAT. You're going to be just fine. But I would say just kind of practice it, or practice with the equations, do some practice problems, and you'll see the degree to which you need to understand this stuff. Don't freak out about the ray diagrams. This is my point. Yeah, I totally agree with what you said there, Humera. That was my exact same sentiment on the ray diagram mess. And that's why I was kind of showing you the way that I draw a lot of this stuff out, because doing quick little drawings like this can usually be, or it can frequently be enough to help you out to figure out your way through something on the test. So one thing that comes up probably is overrepresented on the MCAT in terms of the way that light and optics is tested is kind of sort of like optometry or ophthalmology. So it's worth looking into that just a little bit. If any of you wear glasses or have contacts or anything, and you're aware of what your prescription is, you have a distinct, small but distinct advantage over everybody else on this test. Because if you know what your prescription is, you're already kind of aware of the convention of power of a lens. So if we look at the 1 over F equals everything else, so we're going to say 1 over F equals 1 over I plus 1 over O. That's also equal. This whole thing is also equal to power. So power equals 1 over F. This is also equal to 2 over R being the radius of curvature that we talked about earlier. So if you think about the units of S, the units of power of a lens, they have to be inverse meters, right? Because all of these other things in here are all in units of meters because they're all lengths. They're all distances here. Powers is this unit called diopters, and it's going to be, the diopters are the same as inverse meters, the same way hertz are inverse seconds. All right, so if you do have a prescription, most of you, given you're relatively young people, probably have prescription for correcting myopia, which is nearsightedness. I have the same thing. So my prescription is -6. What that refers to is just like how much help I'm getting to converge light on my retina compared to somebody who has 20/20 vision. If we look at what the eyeball looks like for somebody with myopia, just because this is probably the most relevant to most of you, the eyeball is just a little bit elongated compared to what it would be for somebody who does not have myopia. All right, so we can draw our just like slightly elongated eyes. That's a little ridiculous, but we'll just go with it. Think about how light converges back on the retina. The goal of the eyeball, by the way, is to converge light perfectly on the fovea of the macula, which is like the small, tiny part where you have the highest visual acuity in the retina. If we imagine looking at something really far away, which is going to be the issue for somebody who's nearsighted, then we can think about light rays coming in from far away again. And this is the exact same exercise we were going through earlier. But in our nearsighted person here, we can imagine these light rays converge, given that the eyeball is a little bit elongated, the light rays converge just a little bit too early to where they're not going to form this perfect image on the retina. Okay, this is a lot early, but this person needs a powerful lens. All right, so in order to fix the issue for this person, we're not going to change the shape of their eyeball unless we do LASIK surgery, which is a totally different thing. But we can talk about what that is at some point later if you all want. But what we want to do is give this person a diverging lens because we want these light rays to come together later. And so we need them to diverge from the trajectory that they're on when this person's looking at something far away, meaning that they need to come together as if they had come from a nearby object. Right. So for instance, in this case of this nearsighted person, if we place our object right here, they're not going to have any issue seeing this because now they're taking this sort of angle up to the eyeball. And so given that we have this as our theta 1 now, And remember, we're measuring it with respect to the normal. So like if this is theta 1, theta 2 still has to be a little bit smaller than theta 1, but it's going to be sufficiently large that it can actually make it all the way back to the retina before these things converge. So again, this is our new theta 1 with respect to this one. And so theta 2 is going to take some other angle with respect to the green line, and we end up converging back here on the retina. So that is how lenses correct people with myopia, is they make it to where the light rays from distant objects are no longer parallel when they leave the lens. They are actually like have this trajectory with respect to the interface of the medium that forces the point of convergence for the light rays, or the image in this case, to form on the actual retina. Somebody who has hyperopia, which is the opposite issue, and usually these are a little bit older people. Not that everybody who has hyperopia is old, but frequently there is a trend here. And the reason for this is because the lens in the eyeball, so the lens is located inside of your eye, and its job is mostly fine tuning this thing. Your cornea does 70% of light bending, the cornea being like the front surface of the eye. The lens's job is to fine tune it. So there are muscles that attach to your lens. The lens is this like spongy tissue that wants to form kind of like a ball, but you have muscles attached to it that will stretch it out whenever you need to stretch it out. And so the goal of stretching it out is taking it from being this, this ball thing to now it being like this thing, meaning that and if you think about which of these is going to refract light more, well, you can think about the power of the lens. And as you know, power is inversely related to radius of curvature, which you can see from this equation, right? Because it's inversely related to focal length. And so as radius of curvature gets bigger, and if we look at radius of curvature in each of these, well, radius of curvature in the small one is going to be like here, right? S is power, by the way. It is, I don't remember if it's ciliary muscle or not. Sorry, just answering questions in the chat. But if we look at radius of curvature here, this is the radius of curvature for the balled up lens, meaning that the muscles aren't contracted. And if we look at radius of curvature for this one, where we're imagining the muscles are contracted, we have to draw this is going to be a disaster of a drawing, but we have to draw a big circle. All right, I'm erasing that. That's embarrassing. So the radius of curvature for this flatter one would obviously be way bigger. And so we can imagine that this small one, where it's all balled up, is going to refract light a lot more. So whenever you're looking at something up close, usually in the case of the person who has normal 20/20 vision, when you're looking at something up close, normally you need this lens to be balled up a lot more than if you're looking at something far away, because you need it to work a lot harder to bend the light back onto the retina, right? Whereas if you're looking at something far away, these muscles contract and you don't need it to bend the light so much to get back to the retina. The problem in people as they get older is that they end up having a situation where the lens loses some of its ability to ball up on itself. And so by losing the ability to ball up, it makes them able to see stuff that's really far away, but they can no longer see stuff that's up close. So if you ever see like your dad or your grandma or somebody like hold their phone out and look at it like this as they're trying to send a text message, and they've probably got the font enlarged too, you will notice that is probably what has occurred with their lens. And again, that's not the case. And everybody, okay, I gave my disclaimer. Okay, so that is hyperopia, and these people will need a converging lens to help them out, because then these people, light rays are coming together behind the retina. So that's just what's going on there. I am hesitant to say any questions on that, the eye stuff. Was it power equals 2 divided by r squared? No, it's just 2 divided by r, not r squared. Can you explain the underfunding of the overbidding of light? I have no idea what you're talking about, Yumera. Sorry. You can also just unmute and say it if you want. Not to call you out too much, or if anybody else. The underbending of light. Oh, gotcha. Okay, yeah. Underbending of light. Okay, so whenever when the lens of the eye is unable to contract on itself, unable to become a ball. Yeah. So whenever the lens is unable to become a ball as you get older, it will stay in this sort of like stretched out form that's here. And that just makes it less able to cause the light rays to converge. So I'll just draw it. I'll just draw another picture down here. I end up drawing a lot for the light and optics. So we give them a normal eyeball here. This is kind of difficult to imagine, but okay. So normally the whenever they're looking at something up close, normally, let's look at the case where you don't have an appropriate lens first. So whenever you're looking at something up close, the light rays are coming in like this. And if your lens is not working appropriately, what's going to happen is they're not going to be able to converge until they get way back past the retina. And so normally when the lens balls up, it will cause the light rays here will go through this balled up lens, which is inside the eye. And that will cause them to come together earlier so that they actually do converge on the retina. So that's what's happening in the lens. Okay, I'm not caught up on the chat at all. Sam, are we good on the chat?
Yeah, I think we are.
Okay, all right, cool. Anyway, so that's what's happening in the case of, like, this is what the lens of the eye is actually doing, because you need a little bit different bending of light when you're looking at something far versus when you're looking at something close, just because of the angle of theta 1. Like theta 1 changes if you're looking at something far versus something close up. If any of you have a high prescription for glasses, so I have a prescription of -6, which is like higher than most people. One thing that you'll notice is you have a superpower that you might not be aware of, and that is to see things that are really, really tiny, really, really up close. You have to take your contacts out or take your glasses off, and you can actually like see way greater detail than most people can, but it has to be like really close to your face. So anyway, if you didn't know about your superpower, you should try it out sometime. Anyway, so that is some information about eye stuff. Any other questions on the eye, generally speaking?